Okay, so we are going to continue with the confidence interval topic. In this case, we are going to analyze 3 more confidence intervals. The first one is also for mu, but the difference between this one and the other one that we had is that now the sample size is small, or you don't know the value of this sigma parameter. If you remember, the confidence interval that we saw implies that you already know the value of sigma, or you have a sample size that is greater than 30. If you don't have either one of those requirements, you should use this formula. We would need the mean of the sample, and we also need the standard deviation of the sample, and we are assuming that n is small, that it's less than 30 elements. We should assume that we are taking the sample from a normal population, and to get the confidence interval of some level of significance, we should apply the formula that it's there. If you see, the difference between this formula and the previous one is this element that it's here. This element corresponds to a t-table. We have been using the normal table. However, for this confidence interval, we need a t-table, and I'm going to show you the table in a moment. We have the same elements, the mean, we have the standard deviation, and we have the sample size. So for this t-table, the t-distribution actually has degrees of freedom. In the case of this confidence interval, the degrees of freedom are n minus 1. So the sample size minus 1 is going to give you the degrees of freedom, so you can take a look at the table. This is the table, the t-table. You can see that this table has, in this column, in the last column, you have the degrees of freedom. So here you can find the degrees of freedom, and depending on the table that you have, goes from 1 to around 20 or 30, because if you have 30 degrees of freedom, actually that implies that you have 31 sample size, so you could use the table for the normal distribution. So that's why you don't have a lot of degrees of freedom. The other thing that you should be able to look is this element here. This one here is the value of alpha. So if you want to get a value of t where alpha is 0.05, this is the column that you should look. If you have different values, alpha 0.005, that is the first column, 0.01, 0.025, 0.05, and 0.1. You don't have a lot of values for alpha because, well, we usually have significance levels from 9%, 90%, 95%, 99%. No? So those are the relevant values for t. So here we have the table. We are going to look actually for this column and this, the column and the 20 degrees of freedom. The 20 degrees of freedom are here. And the column is this one. Just let me check that this is the column. No, actually the column is, the column here is this one with these degrees of freedom. So if I take a look here, you could see that this is the alpha that we need, this one. So we have here the value of t, it's 2.086. So let's take a look at an example. So we have an exercise here. It says that, well, there are many treatments for bulimia, but some subjects fail to benefit from the treatment. In a study to determine which factors predict who will benefit from the treatment, some scientists found that self-esteem was one of the important predictors. So they took a random sample and equals 21, so we have a sample size of 21, so we cannot use the previous in the confidence interval, we need to use this one. And they took the post-treatment self-esteem scores, so we have the mean here and the standard deviation here. And the question is about the confidence level for the true post-treatment self-esteem scores. So we are going to use the formula. I think that we could remember that this formula is x bar plus minus the t-value s divided by the square root of n. So we are going to use exactly that, those values. Let's find out the value of t. If you remember, I told you that the value of t require two things. First one, the level. If you see here, this is a 95% confidence interval. This implies that alpha, it's the complement, it's 0.05, and we need alpha half for the table, so this is 0.025. So this is the value that we are going to use. And the other thing that the t table needs, those are the degrees of freedom, that it's n-1. So the degrees of freedom in this case are 20. So we are going to look for t of 0.025 and degrees of freedom of 20. Okay, so we have here the value of t. This is 2.086, and we actually have everything we need to get the confidence interval. We have x bar, that it, well, in this case this is y bar, plus and minus the 2.086 times the standard deviation, that it's 7.4, divided by the square root of 21. So this gives you 23.23, and the upper limit is 29.67. So we conclude in the same way that we conclude for the previous confidence interval, and we will say that with a 90% confidence, the true post-treatment self-esteem score is between 23.23 and 67, sorry. So there you can say, if you have the background of the problem, you could say if this score is low, is high, or whatever the conclusion could tell you. So if you take a look, this is the same approach that we'd use. The only difference here is that we need to use the t distribution because we cannot use the normal distribution because of the sample size. So when you have a small sample size, you should use the t. Okay, so this is another example here. We have some method known as fractional crystallization that it's used to purify organic compounds. So we have an experiment. And they take 10 specimens to be prepared and to produce the substance here. So you have 10 data if you take a look at that, and we want to build again a 95% confidence interval for the mean number of grams that can be recovered from that amount of grams of aniline. So now, before we can use the method, we need to get the mean and the standard deviation of those 10 observations. So we need to remember how we did it in the first part of the course, you should be able to remember that we use the formula where it was x bar was the sum of all the values divided by n, and that s was the difference between each value minus the mean. This was the square, and this is n minus 1. So, well, you can use your calculator. Please remember how to use it, and you should get 3.781 with a standard deviation of 18.9. So we have those values. Now the other value that we need is again t. You have alpha that should be 0.05, and you have alpha half, that is 0.025. However, the degrees of freedom now are different. Actually, we have n minus 1 degrees of freedom. We have 9 degrees of freedom to look at in the table. If you look in the table with 9 degrees of freedom and alpha of 0.025, you have a t-value of 2.262. So this is the one that we are going to use. So we are going to have a confidence interval with 3.78 plus and minus 2.262 times the 0.18 divided by the square root of 10. So if you do the calculations, you will get a confidence interval like this. So again, the conclusion is the same. With a confidence of 95%, the true mean number of grams that can be recovered from 4.85 grams of aniline, it's between 3.65 and 3.908. Okay, so that was about the mean. So we took a look at the confidence interval with n greater than 30, and then in this video we saw how to get a confidence interval with n less than 30. Now we could have some interest in the proportion or in the percentage from a population. So we can use this confidence interval for p with a large sample. So we don't have any options here. We need a large sample to use this p confidence interval. So we have p hat, that is the proportion of success in a random sample with n, size n, that it's large, and of course you know that q is 1 minus p. A confidence interval with this level of confidence for this parameter is shown in the formula that you have over there. So if you know, we are going back to the z distribution, to the normal distribution, because the n is large. So now what we need is the value of p, some percentage here, and then the value of q, you can get it, that's just the failure, and then we have the sample size, and we are going to look at the z table. You should remember, this is a table. You should remember this is one of the tables that you could have for z. So we have the values. The z distribution does not have any degrees of freedom, so we are going to look at just the value of z here in this part and in this part, and then inside we are going to take the area. So we are going to use this table. If you remember, you could look for the 0.05, or you can take a look of the 0.95. That is exactly the same thing, because this distribution is symmetric. So we have here the two numbers, these ones. This is 1.645, because it's exactly in the middle. So this is the one that we are going to use for the calculations. So this is the example that we have, where it talks about advertising, and we are talking about young people that would probably be ready to reach some advertisements that are silly in nature. So some group found that 78% of the teenagers actually understand and enjoy ads that are silly. And well, let's assume that we have this sample size of 1030 teenagers. So we have a large sample size. The question is to find a 90% confidence interval over the proportion that understand and enjoy ads that are silly in nature, and then think if you could say that more than 75% actually enjoy these ads. So we need, for this confidence, we need p hat, that is the estimate proportion. So we would say that this is 0.78, sorry. Of course, Q would be 0.22. And then we need N, that it's 1030. We need the value of Z. Alpha here is 0.10 because we need a confidence interval of 90%, and alpha half it's 0.05. So we are going to look in the table, inside the table, the 0.05 to get the value of Z. Okay, so we have Z of 1.645, and if you remember the formula, this is P, that is 0.78, plus minus the value of Z, that is 1.645, and then this is the square root of, again, P times Q, that is 0.22, divided by N. So if you do the calculations here, you would find 75, 87, and 0.8012. So again, we conclude that with a confidence of 90%, the actual proportion of teenagers that enjoy ads that are silly in nature is between 75% and 80%. So do you think that more than 75% of all the teenagers enjoy ads that are silly in nature? And the question is why? You could say that yes, because the confidence interval actually has a lower boundary, it's greater than 75%. We all know that we could be wrong, and we could actually have a proportion, a true proportion of the population that it's less than 75, but we have a good confidence that it's 90%. So the 90% of the time we would be right, saying that the true proportion it's greater than 75. So as we talk about the sample size from the case of the mean, we could also have a sample size for the proportion. So now the question is other, it's different. We want now a sample size that could capture with some error or some confidence the true parameter. So we are in the phase of building the survey, for example, and we want to know how many elements should the sample have. It has. So we have the sample error again. You fix those values. In general, you fix it that in the error less than 0.10. Some recommendations are between 0.03 and 0.04. Of course, if you want less error, you would increase the sample size. And then you have this proportion, this estimate of the proportion. So we can get this proportion by a sample proportion from previous random sample, if we have that. We could have a pilot test. So we don't know exactly the value, but we take, I don't know, 10, a small sample to have it like a pilot. Or you can use 0.5. So if you don't have any idea and you cannot run a pilot, then just use 0.5. That would give you a good approximation. So we have also the value of Z. See that the value of the normal standard distribution is square. Then you have PQ, and then you have the error square, and you have some recommendations error. So let's solve one small problem about this. Referring also to the problem that we solved, we have some teenagers that now we need to know how many should be interviewed to estimate the proportion correct within 0.02. So we have this is the error. And a probability of 0.95, that's the confidence. So, and the hint here is that we could use the proportion from the previous example to approximate the standard deviation, no? So as I told you, for the formula we need the value of Z square, we need some proportion here, some estimate, Q, and the error square. So we should look at the Z value, Z of 0.005, because you take a look at this one, and this one implies that alpha is 0.01, and then alpha square it's 0.005. So we need this value. We can use the proportion of the example that was 0.78 and Q was 0.22. And we have the error here that is 0.02. And now, well, we just apply the formula. So if you look in the table, again, you need to look inside the table for this area 0.005, and you will find that it's around 2.57. So we have now n that should be 2.57 square times 0.78 times 0.22, and this is divided by the 0.02 square. So this gives you 2,833.5. So it tells you that you should interview more or less 2,834 teenagers. So this is like the double of the one that you have already asked. So for example, if you were actually conducting this experiment, you would need to ask 1,800 more, because you already have 100 and so on. So you don't need to start from zero, but you need to invest more time and resources. So if you want more precision, if you want more confidence, then this value of n is going to increase a lot. So most of the times this is a trade-off between the resources and the confidence that you want, and you kind of balance those to actually have some feasible results, no, with the resources that you have. And finally, we are going to talk about the confidence interval for sigma square. So we have talked about the mean, and for the mean we have two options, with n greater than 30 and with n less than 30. We also talk about the proportion, and we have just one option for the proportion, and we are going to talk about the variance, and we also have just one option for the variance. If you have a random sample from a normal distribution, then this is the confidence interval for sigma square. If you take a look, these values that you have here, these values are new. These values come from a chi-square distribution. If you remember, we talked about this distribution in the exponential and the gamma distribution. However, we didn't actually get probabilities and so on. We are going to use a table for this confidence interval, but this is a distribution as the gamma. This is from the same family of the gamma and the exponential distribution. So in this case, we are going to use just the variance of the sample and the table. You have this distribution, the chi-square distribution, has also degrees of freedom as the t distribution, and the degrees of freedom are n-1 also. So we are going to take a look at the table right now. So this is the table. If you see, it's similar to the t-distribution table because we have in the columns here, you have the values of the alphas here, and then here you are going to take a look at the degrees of freedom. So this gives you also the right-hand side of the area. If you need an area of 0.025, then you should look first for that, and then look in the In this one, we need the 0.95, that it's here, and again 5 degrees of freedom, so this is the number that we are going to use, 1.145 degrees of freedom. Now you see that you have the other part of the table, these ones. Actually, these are the ones that we usually use in the confidence intervals, no? And we have the degrees of freedom. We have some values for the degrees of freedom. If you use your calculator or software, you could find more values for these ones. So let's first find the one that we need. We need 0.025. This was the 0.05, and we have the degrees of freedom as 5, so this is the number that we are going to use. This is the first one, 11.07, and we are going to look for the other one. So let's take a look at one example here. You have a maximum noise level for heavy trucks at 83 decibels. And one way to apply the limit is that requires all trucks to conform with that noise limit. Then you could have another method, and well, if the later rule is adopted, then the variation in the noise level from truck to truck becomes important. Now, because a large value of sigma square, the variation, would imply that many trucks exceed the limit, even if the mean fleet were about 83. So one option is to have this for every heavy truck. The other, less satisfactory method, requires that the mean noise for the whole truck fleet, it's below the limit. So if you are going to apply that rule, you should verify that the variation is small, because you could have a mean that it's around the 83 decibels, but you could have trucks that are great above that level. So they took a random sample of 6 heavy trucks, produced the following noise decibel in decibels, no? So you have the values there. And with that data, we want to construct a confidence interval of 90% for the variance. And now we need first the variance of the sample. And for that variance of the sample, you need to use again the formulas that we saw at the beginning of the course. Or you can use your calculator or Excel or something to get the variance of the sample. If you apply the formula, you should get 0.5027. We need also n-1. N-1, we have 6, so we have 5. These are the degrees of freedom that we are going to look at in the table. We have alpha that is 0.1, so we want alpha half to be 0.05. So let's take a look at the two values that we need. Actually, we need this value, that it's alpha half. So we need the value for 0.05. But we also need another value that it's 1 minus alpha half. So this would be chi squared of 0.95. So we need two values. We don't need to square those values. Actually, the square there is just the notation. But we do need two values, actually, because this distribution is not symmetric. So we cannot use one value and just have the negative sign. So we need to look. So we have the values now. This one was 11.07, and then this one was 1.145. So with those numbers we are going to apply the formula. So the formula was n minus 1 times s squared, and here we divided by sigma squared alpha half. This is sigma, and this is the same denominator, but different denominator. This is 1 minus alpha half. So we are going to substitute the numbers, and you should get 0.227 sigma squared 2.195. So again, we will conclude that the actual variance of the trucks is between 0.22 and 2.19. If we are measuring this in decibels, actually we should say that the variance is not so high. And actually this is variance. So we could take the square root of these values, because if you remember, if you analyze this as the variance, this has square units. So in that case, you are not talking about decibels, but decibels square. So the standard deviation, it's 1.48 here. So we take the square root in the upper limit and in the lower limit. For the lower limit, we have, for the standard deviation, 0.47. So actually the standard deviation, the variation between the trucks, is not so high. So we could actually apply the rule for the mean of the decibels of the complete fleet.